Okay, in this lecture, we discuss the uh, another implementation of the full adder, where we try to minimize the number of transistors for the adder. Last time, we were able to construct the adder with 32 transistors, and now in this lecture, we'll try to reduce those more. What we will do here is that we will try to do a simplification for the sum. Basically, we would like to express the sum in terms of Cout, and that will benefit us from reusing the hardware that we generate the Cout to implement the sum, and that should reduce some of the transistors, the sum of the transistors. So let's see here, if we go to the whiteboard here and use a new whiteboard and see. So basically what we will do is we'll use this expression here, which is that sum equal a b c plus c out prime, uh, ended with a, a, uh, uh, a or B or C. Okay. Now the proof for this is very simple actually. If we wanted to prove it, so here is the sum equals A B C plus the C out. If you express it, it will be from earlier slides. It will be A prime B prime or B prime C prime, or A prime C prime, or with I'm sorry, ANDed with A or B or C. Okay, now this is again A B C. Or now if you expand this, if you open the brackets, you will get something like A B prime C prime or A B C prime. So that's A prime B C prime, or A B C, that is A prime B prime C. Okay, that if you expand the if you open the brackets, and that is basically what this expression can be. It is nothing but A or B, I'm sorry, exclusive or B, exclusive or C, which is equal the sum. Okay, so that is how this, so now this expression is actually, we've proven that this is the sum. Now the idea here is that once you generate, so here is A, B, and C. We generate the sum, the carry out prime, and then we use it to generate the sum signal. And here I get, inverted and get the C out. This hardware, now this hardware, I used it for two purposes. Number one, generate the C out, and number two, generate the sum, and therefore I can save number of transistors. Okay, so let's go back now to the hardware here and see how we're going to do it. Okay, so this is the expression that we just proved earlier, and this is the logic gates of the expression. So you can see here, um, the C out prime, the generated. By the way, C out, it's called a majority function for A, B, C, and the C out prime is called minority function for A, B, C, because it's the opposite. Okay, all right. So you can see here he's boxing this and call it minority because it's C out prime, and you can see what he's generating here is exactly that, the function. Okay, so here we have A, B, A, B, or uh, let's see if we can get this expression, which is actually expressed in previous. It's basically this one here. Okay, if you take out the primes. Okay, so let's see. Okay, we just okay. So basically, what's in here is A or B. Okay, ended with C. Okay, or AB prime. Okay, and this is equal to a C or B, C or A B, okay, uh, prime, which is C out prime, okay, and then you can see the C out prime is um, ORed with, so here is the C out prime, ORed with, ANDed with, sorry, with this one, this gate gives you A or B or C, okay, and this is the ANDing of A, B, C. So the expression that we have finally here is what? Is A, B, C, or A or B or C, ANDed with C out prime, which is what we are implementing, or the expression that we derived earlier. Okay, now let's see if we implement this in the transistor. So this is the gate in the block diagram, or I'm sorry, this is the logic gates, and this is the transistor level. You can see here the C out prime, okay, the C out prime. So here is A, these are A, this is A. So you can see this is A, B, and this is B, and this is C. So what we are implementing here is A, B, all right, or at this point here, which is or um, C, A or B prime. So this is what? This is the C out prime. Okay, and then after we generate it, we take it, we invert it, and we get a C out prime. Now, the C out prime, what we do is that we kind of AND the C out prime, AND it with what? We AND it with A or B or C, AND it with or ORed with A, B, C. So this expression give me some prime, and then I invert it, it becomes the sum. It's basically what we derived in the previous slides. So now you can see that I have implemented the full adder with the output sum and carry and the input A, B, C, and if we count number of transistors, we get 28. That's much better than 32 and much better than we started earlier, 70 plus transistor without optimization. Now, sometimes I can get rid of these inverters, all right, where I can generate just the sum prime and the C out prime in some special adders. And in this case, I can save off transistor number from transistor from 28 to 24. That's a significant savings for number of transistors. Okay. Now, let's say, for example, suppose if we go here, suppose, for example, I have let's test this, and we say that suppose I have A is 1, B is 1, and C is 1. So I'm supposed to get a sum of a 1 and a carry out of a 1. So this is sum and this is carry out. Let's see how the circuit reacts. So this is 1, 1, 1. Okay, so you can see here that what? That we will drain the C out to the ground because this will be on. Okay, we'll drain it to the ground. So this becomes what? This becomes a 0, and then the C out is 1. Now, because this is a 0, this is off, right? But since A, B, C are 1, so I'm going to drain this to 0, and the sum after the inversion will be 1, which is what I got with the mathematical computation. So the circuit generates C out of 1 and a sum of a 1. So it's just one example where you can trace them. You have to get used to tracing the output of these transistors. In other words, I might give you in the exam input patterns, and I say what is the value of the sum, what is the value of the carry. Okay, all right. Another type of circuits where we use here is using the multiplexer to implement functions. For example, here, let me just take a minute here. Multiplexers are very powerful in implementing functions. So let's say, for example, um, um, I have the exclusive OR. Say A exclusive OR B, okay, and we will call this is the P function. This is equals to what? A, B prime, or A prime B. Okay, I can implement this is with a multiplexer where I can have, for instance, I can have the B as a select signal, right? And the A as data. So when B is 0, I have A. When B is 1, I'll have A prime. So what I have here in terms of output, F equals or P equals A B prime or A prime B, which is A exclusive or B. So this is the function. So now I can also implement A exclusive or B exclusive or C. Okay, so now notice that here what I could do is that I can assume that this is one function here. Let's just assume this is P now. So this is equals what? This is equals P C prime, or, so notice that the P I already derived it here, right? Or P prime C, okay? And in this case, I could use the P as a select for this mux, right? And here is, and this is here a C and C prime, and this is the value of the sum. So the value of the sum equals what? It is equal to P prime C or P C prime, which is equals to, the P is what? A exclusive or B prime ANDed with C, or A, excuse me, exclusive or C dot C prime, which is equal A exclusive or B exclusive or C. Now, what is the point of all of this? The point is that I use the multiplexer to implement the functions. And multiplexers are known to have least number of transistors, and therefore I can reduce number of transistors. Okay? Okay, and so let's see here back to the adder, and we'll see that the adder generates A exclusive or B, right, which is right here, which is the P, and then this is, and the P prime, which is A exclusive nor B, and using the C signal generate the sum. Now let's take a look how we will generate the exclusive OR gate in terms of the transistor level. Okay, so here we go back and um, we here, let's see, if we draw the exclusive OR gate. Okay, now, so in terms of the here's the P signal that is we use in the circuit that we are examining. We generate A exclusive or B. Now, which is equal to A prime B or AB prime. So now we can use, for example, the A as a control signal for a 2-to-1 multiplexer, okay, all right, and generate this P signal. Or I can use the B, um, the B as a control signal. Okay, so let's see. We can design it as such. So this is here, for instance, I have A as a control signal, and I have here A prime, and I have here A as well. Or I can have, and one of the input A will allow B prime, or here obviously it's a PMOS, and here the A prime will allow B. So if we look at the logic here, this will be A B prime or A prime B. I can use the B as a control signal, so this is B, and this is here B prime, and this is here as well B, and then here this is A prime, and this is B. So the function here, B equals A B prime or A prime B. Both of these implementations are okay. In your circuit that we are studying, they are using some kind of a mix of the two circuits to allow the generation or the easy generation of P and P prime. So here is the circuit that they are using. Oops, sorry. Okay, so let's see if we draw this like so. Okay, so we have here, this is a transmission gate. Okay, and we have A prime, all right, and we have here A. Okay, and this is B here. Okay, and here we've got a B and A prime and B and A. Okay, and this is the P. And again, they chose this implementation. It's a multiplexer, by the way, this one. It's a multiplexer, but they chose this implementation so that they could generate P and P prime easily. Now, you can see what we have at hand here. So let's take a look at our truth table. Uh, the truth table, I have A, B, and let's see what are we generating in terms. So 0, 0, 0, 1, 1, 0, 1, 1. Let's take the case when first case. Let's take the first case when both A and B zeros. When both A and B are zeros. In this case, what you have here is um, this one will be on, right? And um, as well as this one will be on, right, when both A and B. And we will write a zero value for the P, because if this is on, B is 0, we will be writing a value of a 0 to the P. Similarly here, we will be writing a value of a 0 to P. So the value here equals 0. Okay, so let's see the case when both, when uh, uh, A is 0 and B is 1. So this case here, okay, so again, this will be on as well. This will be on as well, and we will be writing a 1 all the way to P. So P is equal to 1, okay? And here we will be writing as well a 1 in this side as well. There will be a 1 here going through this all the way to here as a 1. So you will have one is written from two directions. Okay, what happened when A is 1 and let's take a look here. When A is 1 and P and B is 0, when A is 1 and B is 0, that's the third combination. And we will see that this is A is 1 and B is 0, which is this one here. So this will be on, and you will have a 1 written to the P here, okay? And therefore you will have a value of a 1. Okay, so the B is 0 will have this PMOS on, and the value of the A, which is 1, will be written to the output. Final combination here, when we have, for example, 1, 1, which is the fourth combination. So 1, 1, this will allow this transistor to be on. This is a 1 here. So we will allow this is uh, uh, okay, so A prime will be 0, sorry. A prime will be 0 since A is 1. This will be on, so we will we'll write a 0 all the way over here, so P will be 0, and therefore this one will be a 0. If you look at this truth table, it is P equal A exclusive or B. So this combination of multiplexing is used in notes, and it's used to generate P, and it is very easy to generate as well the P prime. Now the question is, why do I need the P prime? I mean, the answer is we need the P prime because once I generate the P and the P prime, it's easy to generate the XOR. So as we said in the previous slide or a previous whiteboard, before I erase it, um, you have here you have here the sum equals A exclusive or B exclusive or C. What we did, we agreed, we said let's name this as P. Okay, this is as P. So this is equal to PC prime, or let's say P exclusive or C, okay, which equals the P prime C or P C prime. So once I generate the P and the P prime, I generate the P and the P prime. Now what the way I can generate the sum is this, the following. So this is my sum. Here are my transmission gates. So now I can feed off here. I can feed off here the C prime, and here I have the P prime, okay, and here I have P, and here I have P prime. Now you can see here the sum is generated through a multiplexer using P, P prime, and C, where P is A exclusive or B. And now we go back to the notes after this discussion, okay, and you can see exactly what we were talking about in the notes. So now it is clear to you how we are generating these P and, oops, sorry, let's see if we can get this straightened out. See, okay, okay. So you can see how we generated P and similarly P prime, and how we, from this 2-to-1 multiplexer, we generated the sum and the sum prime. After the inversion, it will be a sum prime. So this is a 2-to-1 multiplexer using the P and the P prime as control signals and the C and C prime to generate the sum, as we have indicated earlier. Now for the C out, it turned out I can use the P and P prime. Let's just use a different color here. I can use the P prime and the P, all right, using the A and the C signal that to generate the C out. So you can see here the P and the P prime for the 2-to-1 multiplexer used for the C out, and coming to you here the signals, which are the C, and of course we are using here A prime and C prime, so that I generate the C out prime, and then I can invert them afterwards. And so you can see this is the gate diagram. This is the transistor. You can see here clearly the P prime, right, and the P here, and going inside here you will see the A prime, right, and the C prime. Okay, so at this point what you have is the C out prime, and then after the inverter the C out. All of this gives us a 24 transistor number of transistors in the circuit, which is pretty small, as we have discussed, compared to the others. Remember, we went from 72 to 32 transistors to 28 transistors to 24 transistors, and then this is another 24 transistor circuit for this type of implementation.